In the previous lecture, we introduced electric fields as the force per unit charge that a test charge feels near another charged object. In other words, if we put a test charge near a charged object, it experiences a force, which we can determine from the electric field. However, you might be wondering how we would actually move a charge to this spot in the first place if it experiences a force away from it. In reality, to do this, we would need to push against the Coulomb force ourselves in some way, and then hold our test charge in place. Both of these actions require energy. You might also wonder what happens if we let go of the charge from where we are holding it. If we do this, the charge instantly starts accelerating in the direction of the field lines, which means that it has a kinetic energy. But where did this energy come from? So far, we've established why a charge moves like this, but we haven't yet thought about how much energy it has. Electricity isn't just about moving charges around. It is about doing work, storing energy, and converting it into something useful. In this lecture, we will discuss the energy that a charge has while in an electric field, and introduce a powerful new concept known as the electric potential. Let's start by thinking again about our point charge system. So far, we've established that a point charge, which we'll label Q1, creates an electric field like so, and that a positive test charge experiences a force in the direction of the electric field. Now technically, so far we've just been looking at a freeze frame of this system. In reality, as soon as there is a net force on the object, it will start accelerating. This is simply because of Newton's second law, where the net force on an object equals the mass of the object times the acceleration. Now, we haven't actually spoken about mass throughout this lecture series, as we've been trying to keep things as simple as possible. Of course, however, if the mass of our test charge was 0, the acceleration would be infinity. So, for the sake of completion, we'll just say that our charge has a mass, like any other real object. It's not really that important for this lecture, but it is worth highlighting again that in reality our test charge would have other forces involved, such as gravity. That being said, in electrical circuits, we'll see that it is actually the electrical interactions we've been talking about that dominate, so our seemingly unrealistic examples aren't so far-fetched. But we'll get to all that in the next lecture. Anyway, as our charge has now been accelerated, it is moving with a velocity v. Therefore, we know that it must have a kinetic energy. As energy cannot be created or destroyed, we also know that even before we let go of our charge, it must have had an energy of some sort. We say that our charge had a potential energy, specifically an electrical potential energy. We define the electrical potential energy as the energy a charge has due to its position in an electric field. It is denoted by the symbol U, and it has the units joules, like any other form of energy. Now, if we let go of our test charge and allow it to accelerate along the field lines, clearly it is gaining kinetic energy. If it is gaining kinetic energy, it must be losing potential energy. Let's consider 2 points along a field line, which we'll label R initial and R final. If we let go of our charge at R initial, let the field accelerate it a little, and then stop it again at R final, we can say that the potential energy of the charge has decreased. We can say that the change in potential energy, delta U, is the potential energy at R final minus the potential energy at R initial. This should all seem intuitive. Now, to continue further, we need to return to a common concept in classical mechanics known as work. The work, or work done, is just the energy expended when moving an object along a path. In our system, as we let go of our test charge, the electric field is doing work on it to move it from the point R initial to the point R final. The work done by the electric field is simply minus the change in potential energy when moving the charge from R initial to R final. Now, the formula for work done can cause a lot of confusion. It is often written as the force required to move an object along a path delta R times delta R. However, as we know, the force and displacement are vectors, not scalars. We therefore instead express the work done as a dot product between F and delta R. For those unfamiliar with dot products, there are a lot of great videos out there explaining it, but it's basically a measure of how much a vector maps onto another. But in simpler terms, it is just each vector component of F times each corresponding vector component in delta R. Alternatively, it can be written as the magnitude of F times the magnitude of R times cos theta, where theta is the angle between the two vectors. In our example, the direction of F is the exact same as the direction of our path delta R, so we can just write F times delta R. We can say that this equation only applies when the force is in the same direction as the displacement. But there's still a problem with this formula. That is, what force do we actually use? As we are considering the work done by the electric field of a point charge, we obviously use the Coulomb force. But the Coulomb force changes as our test charge moves further from Q1. Our current formula for work actually only applies when the force stays fixed across the entire path. We can get around this by dividing our path into smaller segments. If we do this, we can say that the total work done by the field is just the sum of each chunk of work done while moving the charge over each small segment. It is also equivalent to the area under a plot of the force against displacement. Here I have plotted the side of the Coulomb force as we move away from Q1. For each small segment, the work done is just the force times the displacement of that segment, so the dot product of F and delta R, where F is just the Coulomb force at the midpoint of that segment. So the total work is the sum from the initial starting point R initial to the final point R final, of the forces dotted with each segment's displacement. The more segments we take, the more accurate our result for the work becomes. To get the exact result, we let delta R tend to 0 to become dr, so that our sum becomes an integral over F with respect to dr, from the starting point R initial to the end point R final. This is the real formula for work done. It's always the area under the force versus displacement curve. Let's evaluate this for our point charge system. Now, as our infinitesimally small amount dr is a vector, we can write it as the magnitude dr times the direction dr hat, which is just equal to the direction r hat. As we already said, here the displacement of each segment r hat is always the same as the direction of the Coulomb force. In this example, we have used a straight field line, so this is pretty obvious, but it actually applies to any field line, no matter how curved it is, as at each point along the line, the force due to the field is always in the same direction as the displacement. So we get the dot product of r hat with r hat, which is just 1. This is a key property of the dot product, so if you're unsure of this step, do try and understand it yourself. But this is really neat, as the vector part of our equation now completely disappears, which simplifies things greatly. We now just have to integrate the magnitude of the Coulomb force with respect to dr. To solve this, we simply take the constants outside the integral, such that we get the following expression, which is work W equals Q1 Q2 of 4 pi epsilon naught times the integral from R initial to R final of 1 over R squared. This integral is an easy one, equal to minus 1 over R, and we can apply the limits like so. If we expand the brackets, we can write the expression as follows. This is the work done by a point charge Q1 on a test charge Q2 when moving it from any position R initial to another position R final. Now, as we've already established, the change in potential energy of our test charge during all of this is equal to minus the work done by the field. Therefore, the change in potential energy is simply minus this expression. Now, we also decided that the change in electrical potential energy is the potential energy at R final minus the potential energy at R initial. Now, if we look at our expression, we can say that the potential energy at R initial, which we logically expect to depend on the position R initial, is Q1 Q2 over 4 pi epsilon naught times R initial. and that the potential energy at R final is Q1 Q2 over 4 pi epsilon naught times R final. More generally, we can say that the potential energy anywhere in our point charge system is just a constant times 1 over R. This is our expression for the electrical potential energy of a test charge in a point charge's electric field. We can also derive a more general expression for the electrical potential energy in any system using a very neat trick. Firstly, let's return to our expression for the work done, which is just the integral of F dot dr. If you remember from the last lecture, we can also write the force as the test charge Q2 times the field E at that point. We can therefore write the work done by an electric field as Q2 times the integral of E dot dr. We can write the change in electrical potential energy as simply minus this. Now, delta U is just the potential energy at R final minus that at R initial. But what if we could choose a point in space where we knew the electrical potential energy would be zero? Well, this is a tricky task, as if you recall from lecture 2, every charged object in the universe is connected to every other charged object. But we can also say that as we move a charged object infinitely far away from another, its interaction will approach zero. Therefore, if we set R initial to be infinity, we can say that the potential energy there is zero. So, our change in potential energy would now just be equal to the potential energy at R final. Substituting this in, we get the potential energy at R final equals minus Q2 times the integral of E dot dr from infinity to the position R final. This is the real equation for the electrical potential energy. The electrical potential energy is the energy required to move a point charge from infinitely far away to a measurable position in the electric field. This equation works for a test charge in any electric field. If you apply this to our point charge system, you'll get the same equation as before. Now, let's return to another system we discussed in the previous lecture and see if we can figure out these quantities for it. It can actually be a little confusing to deal with this one, so it's worth going through. As we said before, the parallel plate capacitor is one of the few systems that has an approximately uniform field between the plates. To be clear though, this is not the case outside the plates. So when considering our electrical potential energy, we should only consider potential energies in positions between the two plates, using our electric field formula. Let's consider the change in potential energy when moving from the positive plate to the negative plate. We'll say that the position of the positive plate is R equals 0, and that the negative plate is at R equals D, which is just the distance between the plates. Doing this, we get a change in potential energy of minus Q2 times the integral of E dot dr from 0 to D. As E is just a constant times the direction R hat, which is of course in the direction from the positive plate to the negative plate, E dot dr is once again just a constant scalar E times dr. Evaluating this integral, we just get E times R from 0 to D, and if we expand this, we get minus Q2 times E times D. This is another very neat formula. We can similarly say that the work done by the capacitor on the charge, when moving it from the positive to the negative plate, is simply Q2 times E times D. Lastly, we can say that the potential energy at any distance r between the plates is simply the integral from r equals 0 to r equals r final, which just gives minus Q2 times E times r final. Now, if we were to assume that the field follows this equation everywhere, even outside the plates, and we try to find the potential energy from infinity to a point r final, we would find the energy to be infinity, which is obviously wrong. This is simply because our equation for the field is inaccurate besides the region between the plates. It's quite neat how the mathematics automatically lets us know about this. I'm aware that we've mentioned quite a lot of equations over the last few minutes, so I'll quickly summarize what means what. Firstly, the general equations, which apply to a test charge in any electric field, are as follows. The work done by an electric field on a test charge Q, when moving it from a point R initial to a point R final, is Q times the integral from R initial to R final of the dot product between the electric field and dr. The change in the electrical potential energy when moving from R initial to R final is simply minus the work done by the electric field. The potential energy at a given point, such as R final, can be found by moving R initial to infinity. Now, if we apply these equations to a point charge system and the area between a parallel plate capacitor, we get the following results. I'll also note that if you want to find these quantities for a point charge around any other charged object, all you need is an equation for the electric field due to that charged object. Everything else can be worked out from that. Now, you might be wondering where we are going with all of this. In the previous parts, we already introduced a lot of new mathematics for understanding charges, and now we have even more to think about. Well, it turns out that considering how the energy of a test charge varies throughout an electric field is rather useful information, and it intertwines quite beautifully with our concept of the electric field. We are going to introduce one more mathematical quantity, but I promise it is the last one for now. If you remember in the previous lecture, we defined the electric field as the force a test charge experiences divided by the test charge. We can similarly define something called the electric potential, which is equal to the electrical potential energy divided by the test charge Q, or Q3 in this example. As U equals minus Q3 times the integral from infinity to R final of E dot dr, the potential is just the integral of minus E dot dr. As the units of potential energy are joules, and the charge is in coulombs, the units of electric potential are joules per coulomb. We also decide to introduce a special unit just for the potential, known as volts, which is equal to joules per coulomb, and denoted by a capital V. If you were curious, the volt is named after Italian physicist Alessandro Volta, who was the inventor of the battery. We'll speak about batteries later in the series. The electric potential simply describes a charge's position in an electric field. We can also define a quantity known as the potential difference between 2 points, which, as you might have guessed, is simply the change in potential energy divided by Q. The potential difference is also known as the voltage. This is written as delta V and is equal to the potential at a point R final minus the potential at a point R initial. In terms of the electric field, this is simply minus the integral from R initial to R final of the electric field dot dr. In other words, it is minus the area under the electric field curve. This is equal to the change in potential energy over Q3. Lastly, as the work done is just minus the change in potential energy, the potential difference is also minus the work done by the field divided by Q3. So why do we care about this quantity we've just made up? Well, it turns out that measuring how the energy of a test charge varies throughout an electric field can give us some very interesting information. Here I've plotted the electrical potential at each point in space for a simple point charge using colour. Red represents a positive potential, green represents a zero potential, and blue is a negative potential. In this system, the potential tends to zero as we move away from the point charge Q1. As the potential energy depends on 1 over R, you can see that it gets close to zero pretty quickly. To be clear though, the potential is still varying throughout the green areas as we move further away from the charge. As we do this, we find that there are lines in space of equal potential and equivalently equal potential energy for a given test charge. If we were to locate these regions in a simple point charge system, we find that they are concentric circles around Q1, or spheres if we were to consider the system in 3 dimensions. We call these lines equipotential lines, and as the name suggests, they basically indicate where the potential is equal in space. In 3D, we just call them equipotential surfaces. These work exactly like a contour plot on a map, where the lines indicate areas of equal elevation. Here's a slightly more interesting plot for a system of 2-point charges. Here we find that the potential is more positive near a positive point charge, and more negative near the negative point charge. What's really interesting about equipotential lines is that they are always perpendicular to our electric field lines. This makes them somewhat intuitive to sketch, especially if you already have a good guess of the field lines. It's very neat how the existence of a charge in nature leads to this mathematical grid of field and potential. Throughout the entire universe, and certainly the world we live in, there is this invisible but very much real grid caused by charges existing in nature. Right now, we're all in an electric field with equipotential lines, and always will be. It is important to remember that unlike the field, the potential is a scalar quantity rather than a vector. When we let go of a positive test charge, it always moves from the most positive potential region to the most negative region. It will do this by directly moving along the field line it lies upon. There's one more really neat trick we should mention about calculating potential while working with point charges. If you remember from before, for a system of multiple point charges, the total electric field at a point in space is simply the sum of the electric field due to each individual charge. This is also known as the principle of superposition, and it can similarly be used when talking about potentials. If we wanted to find the potential at any point in space, we would write minus the integral of the total field E with respect to dr from infinity to this point r. If E is just E1 plus E2, we can write our integral like so. We can then split this into multiple integrals over each field component. As you can see, each of these integrals represents the potential contribution due to each point charge. So, we can rewrite the total potential as simply V1 plus V2. This is a very powerful result, and we will use it a lot when building electrical circuits later on in the series. We can sketch equipotential lines for our parallel plate capacitor as well, which, as you could guess, are just evenly spaced lines perpendicular to our field lines. In this neat example, the potential decreases linearly from the positive plate to the negative plate. As the potential energy is minus Q times E times D, the potential difference across the plates is just minus E times D. Similarly, for any point between the plates, the potential is just minus E times R. Now, you might have already figured out what I'm about to say already from your intuition, but there's actually one more very neat equation we haven't yet mentioned. As we said earlier, the general expression for the potential is minus the integral of E with respect to dr. The integral of E with respect to dr is simply the area under E, and we consider the potential at each point in space is simply minus the area up to that point. There is another neat thing we can say here though, which is that the electric field is equal to minus the gradient of the potential. In this simple example, where the field is constant, this is just minus the change in V over the change in R, or minus V over D, as we already found. But let's go to a more complex example, such as the positive test charge, where the electric field changes with R. We'll consider the field along one dimension, which we'll label X, to keep things simple. If we plot the electric potential now, we'll get this, and the electric field is simply minus the gradient of V. Therefore, in one dimension, E equals minus dV by dx times x hat. If we were to consider all three dimensions, we would just write the electric field along each dimension as the gradient of V with respect to that spatial dimension. In other words, minus dV by dx, minus dV by dy, and minus dV by dz make up each vector component of the field. When doing this, we use these partial derivative symbols, where we use a curly d rather than a regular one. All this means is that when you take each derivative of V, the other spatial dimensions are treated as constants. This mathematical operation is also denoted by the so-called nabla symbol, which is just an upside-down delta symbol. So, E equals minus nabla V. Don't get too intimidated by this, it's just a convenient way of writing the gradient of V in each spatial dimension. Just remember E as minus the gradient of the potential. This equation means that the electric field always points towards the more negative potential regions, which makes complete sense. The steeper the potential gradient, the larger the field is. So, let's now summarize the key points of this lecture. Here are the general equations for the electrical potential energy, change in electrical potential energy, and work done by any electric field. The electrical potential energy tells us how much energy a charge has in an electric field. Applying this to a point charge system and the region between a parallel plate capacitor, we get the following expressions. The electric potential is simply the electrical potential energy of a test charge divided by the test charge. The general expressions for the potential and potential difference are as follows. Applying these expressions to a point charge system and a parallel plate capacitor again, we get the following results. We should also note that there are regions in space of equal potential, known as equipotential lines and surfaces. They are always perpendicular to field lines. Lastly, the electric field is also equal to minus the gradient of the potential. Overall, this lecture has told us how the energy of charges vary as they move in an electric field. I'm aware that this all seems rather abstract and quite far from reality. We now have a lot of mathematical expressions for understanding how charges interact with one another, including the forces they induce, how they influence the space around them, and their energies. This is all well and good, but you might be wondering where we are going with all of this. The question remains, how can we use all of this theory to our advantage? In the next lecture, we'll see that the potential difference isn't just a number, and that electric fields aren't just imaginary lines in space. They are in fact key quantities for building useful, real-world electrical devices. We will see that by setting up potential differences, we can manipulate electrons to transfer energy from one place to another.